Good afternoon, everyone. My name is Alalea and I'm a UKRI Future Leaders Fellow at the Department of Civil and Environmental Engineering at Imperial College London. So as Steve mentioned, the core of our research is developing new types of permeable pavements that can address flooding and, in general, extreme weather events. So in terms of my background, I'm a civil engineer and a material scientist, and in the past 7 years, I've been working on permeable concrete pavements, their benefits, their challenges, and why they are not really widely adopted despite their benefits. And without further ado, I just go through my presentation. So I will first of all talk about urban flooding and then lead on to conventional permeable concrete pavements and their challenges. This will be followed by the development of a new type of permeable pavement, which we call it clogging-resistant pavement, or also known as Keyacrete, and I've got a little sample of it here if anyone wants to have a closer look at it. And the focus of today's talk would be the freeze-thaw durability of this type of pavement, because that's very important for permeable concrete pavements. And I will end the talk today by going through the contributions of this pavement to net zero. So there is no need to mention that flooding is a huge challenge, and we've seen in the past couple of months how extreme weather events have an impact on our day-to-day life. So the cost of flooding is projected to increase to £500 billion by 2030, and hence there is a clear need to do something about this and develop infrastructure that can address this sort of extreme weather events, as climate change is not really helping and is increasing the chance of these events by 59%. So conventional permeable pavements are a form of sustainable drainage systems to address urban flooding by absorbing stormwater runoff. However, they have a number of challenges which we've been studying in the past couple of years. So the first challenge is that they're highly susceptible to clogging. This is blockage by sediments over time as they're being used. The second challenge is that they have low strength. They can only be used in low load-bearing applications, and as I'm sure you appreciate, the heavy load-bearing scenarios like highways and airports also need solutions like this. And the final challenge, which would be the focus of today's talk, is the poor freeze-thaw resistance. So first of all, let's have a look at some of the data that we have in terms of susceptibility to clogging. So this is the buildup of debris on the pavement over time. So we have the pavement as cast on the left-hand side, and over time, as the pavement is in service, it gets exposed to sediments like sand and clay, which are the most detrimental ones, and it blocks the pavement. So we've done a lot of testing on not only the laboratory-prepared pavements, but also the commercially available ones. And we've exposed them to what we call accelerated clogging tests, so what these pavements would be exposed to over their service life. And you can see, depending on the pore structure of the pavement, between 11% to 32%, you get clogging between something like 3 cycles up to 7 to 8 cycles. So this is a very bad news for permeable concrete pavements, because it means that within a year they become fully blocked and you need to maintain it. And this maintenance is something that, talking to the transport authorities in general, they don't want to do, because it means that closing off a section of a road, or it means that it's going to be a lot of cost, not to mention that it's also going to damage the pavement surface over time. The second challenge is the pavement strength. So the compressive strength of this type of pavement ranges between 6 to 32 megapascals, which is good if we want to use this pavement for low load-bearing scenarios like a driveway or a car park or even a cycleway, but you can't really use it on highways, airports, or any other critical infrastructure. And that means that their application is going to be severely limited, and other scenarios cannot really benefit from this type of pavement. So in order to address these two challenges, and also the freeze-thaw, which I will mention in a moment, we developed a new type of permeable pavement, which is called clogging resistance, also known as Keyacrete. So we completely changed the pore structure of this type of pavement. So we engineered a new type of pore structure, and we also are using a much higher strength cementitious mix. And this cementitious mix can change and can be altered depending on the application. And in the past number of years, we've been doing a number of tests on it to understand its performance. So if we quickly have a look at this video, so both of these pavement sections, on the left we have the conventional permeable pavement of 20% porosity, and on the right we have Keyacrete of 20% porosity as well. Neither of them are clogged. So as we expose the conventional pavement to the same volume of water as Keyacrete, it quickly becomes overwhelmed by the amount of water that it's receiving, and we need to remove the water source. But as in the case of Keyacrete on the right, you can see that it's capable of receiving that volume of water almost indefinitely. The reason why that is the case is because the conventional permeable pavements have what we call a tortuous pore network. It means there is an indirect pore network. So if you get sediments blocking this section of the pavement, the rest of the pavement becomes completely impermeable. And when we try to maintain them, the maintenance only cleans the top couple of millimeters of the surface. So within a year, that becomes blocked up again, and then you need to clean it over time, and every year that requires that cleaning. Whereas in the case of Keacrete, you have direct channels going through the concrete, and that means that the sediments and the water can go through immediately from one side to the other. And that's why at the moment we have a lot of interest from India, because this type of pavement is the only pavement that can address monsoon-type flooding. And it will also benefit their drought situation because it recharges the groundwater table. So just to show the clogging resistance performance of this pavement, so we have tested this pavement of different porosity between 2% to 30%, and we exposed it to 13 cycles of sediment exposure, the same way as the conventional system. And you can see the permeability is more or less constant throughout the exposure to sediments, which is very promising for us. And typical permeable pavements are lying within this range, the lower end. So the permeability is 10 times higher than what you would expect in conventional permeable pavements. And the added benefit is that it can keep that permeability over time. The second benefit is the increased strength. So the strength of CRP or Keacrete is twice as high as the conventional systems. And in addition to that, that strength can even be increased by reinforcing it, either with fiber reinforcement or steel bars. This is something that the conventional permeable pavements cannot benefit from because of the contact of water and reinforcement causing corrosion and damage to the pavement. But because we changed the pore structure of permeable pavements, we can actually achieve that. And not to mention that we can change the pore structure, change the concrete that we are using just to play with the different parameters that are needed. So as I mentioned before, the focus of today's talk is going to be freeze-thaw resistance. So these are the samples we tested for the conventional permeable pavements and CRP in the lab, just to look at how the freeze-thaw performance compares. So we followed the same procedure as is recommended in Eurocodes. So we exposed both types of samples of different porosity to 56 cycles of freeze-thaw. So that meant 8 hours of freezing it in minus 20 degrees Celsius, and then 4 hours of putting it in a water bath just to expose it to one cycle of freeze-thaw. And then we looked at the performance of both types of pavements. So the things that we measured was change in mass, durability factor, the change in area using image analysis, ultrasonic pulse velocity to understand the microcracking, and compressive strength. So this is what we observed in terms of change in mass. So on the y-axis, we have the mass of the samples of different porosity, and on the x-axis, we have the freeze-thaw cycles. So depending on the porosity of the permeable pavements, lower the porosity, the less loss in terms of mass. Higher the porosity, as you would expect, it loses more mass. So in the worst case scenario, when it had about 30% porosity, it lost more than 50% of its mass, which is quite detrimental, because in real life, that meant that you need to completely resurface that pavement. Whereas in the case of CRP, it kept its mass. And we've done some image analysis and looked at microcracking as well, that the performance didn't change when it was exposed to the different cycles. The next thing we looked at was durability factor for both of the types of samples. Because for CRP, the durability factor was very high, the mass loss wasn't measured at all. It was mainly more than 96%. We didn't need to do this durability factor. But for the conventional systems, we plotted what the durability factor is against mass loss. So for example, for a 2% mass loss, we compared, depending on the porosity, what would be the durability factor, which obviously the lower the porosity, the higher the durability factor, because it meant that it's a much stronger mix and you don't get this cracking and spalling of the aggregates from the cement paste. Then we looked at the change in area. So we scanned the different samples of all of its surfaces and tried through image analysis techniques, measured the area left after 56 exposure cycles. So this is the conventional system, the 30% sample at the start, and this is after 56 cycles when you can see a significant area of it is lost. And at the bottom, we have CRP. And in case you were wondering, we didn't just copy and paste the same image twice. So this is actually what the behavior was after 56 cycles. And this is just a plot showing the change in area with freeze-thaw cycles. And you can see typically after 12 cycles, the mass changes dramatically, because that's when the cement paste becomes weaker and it cannot take any more pressure and it spills away from the aggregates and damages the pavement surface. We also looked at the behavior using ultrasonic pulse velocity, so sending a pulse through the pavement, and obviously the more cracking that you have, the longer the distance and the lower the pulse velocity. And the higher the porosity, the harder it was to measure that. In fact, after 17 cycles, we couldn't measure any more ultrasonic pulse velocity because the pavement was quite badly damaged. Whereas in the case of CRP, again, you can see the measurements are quite constant. So the actual internal structure wasn't affected by these extreme cycles. The final comparison was the compressive strength. So for the conventional systems, it ranged from 4 to 25 megapascals for porosities of 16 to 36%. So that's when they are exposed, not exposed to freeze-thaw. And when they were exposed to freeze-thaw, it reduced by 75 to 96%. Whereas in the case of CRP, so still the compressive strain ranged from 12 to 60 megapascals for the different porosities, irrespective of whether it was a control sample or a freeze-thaw sample, so which was very promising for us to see that. So the next stage for us was, okay, we do this in the lab, that's great, but how can we actually deliver this on site? So we deployed, we went through a number of different design iterations, what would be in terms of material saving, for it to be lightweight, for it to be easily transported on site. And we developed an interlocking tile system that we patented it internationally, and is the picture that you see there, to develop it on site. And we recently developed it at Imperial's White City campus. So our White City campus is known as an innovation campus. So they approached us and said that at the right main entrance, we want to showcase this research, and we want it to act like a drainage site. We are not going to implement any other drainage at the main entrance and just see how it behaves. So we delivered this at the height of the pandemic in summer 2020. And the results was this. So this is the final product. So that's the plan view, and that's the side view looking at the north side of the campus. And in the past 2 years, we've been measuring its durability and its permeability performance. So about a couple of weeks ago, after 2 years of being in operation, and it's a construction site, so it's exposed to a lot of sediments, we decided to pour water on top of it and just to see how the performance is. And as you can see, all of the water goes through it almost immediately. Sorry. In terms of observing its durability performance, so we've been monitoring it using drones. We are taking picture at every square, and then we are doing image analysis just to see whether there are any micro cracks or any sort of damages on the surface. It's been exposed to snow and to the heat waves, and we've developed our own permeability setup such that we can expose the pavement to a lot of water and then see how the performance gets affected. And this is its durability in the past 2 years. So there are ups and downs depending on the moisture content of the soil and how much rainfall it was exposed to, but you can see more or less the permeability is constant despite being exposed to a lot of sediments. So just to wrap it up in terms of its contribution towards net zero, as that's something that is on everyone's agenda at the moment. So first of all, we have reduced emissions from material saving. So essentially, we have a concrete that has a lot of holes, and that density can change depending on the application. So we are saving a lot of material and a lot of concrete. It has a much longer service life. It's been in operation at our White City site for 2 years, and we didn't need any sort of clogging maintenance, which a conventional system would need 3 times at least in a year. So, and that shows us that we've been forecasting a service life that is going to be comparable to a normal concrete surface. And we are using recycled material within the concrete and also within the matrix that makes those pores. It contributes to flood mitigation, which is very important at the moment with climate change. We know that our infrastructure have to be resistant against extreme weather. It can reuse water. So recently, I've secured £3 million from Royal Academy of Engineering and UK Research and Innovation to apply this technology to highways and airports. And one of the important things for them is water reuse. For example, how can the water that goes through it be stored and be used by the terminals nearby? And another important factor is that it decreases the urban heat island effect. So the amount of water that it absorbs cools down the pavement, not to mention that in comparison to asphalt pavements, it has a much lighter color as well, which contributes to that. So just to summarize what I mentioned today, so climate change is a serious factor, and it's going to increase the likelihood and severity of extreme weather events. Conventional permeable pavements are a good solution, but unfortunately they have a number of challenges, which meant that they are not widely adopted as much as we want to. We've engineered a new type of permeable pavement, and we've shown that it works by our trial site at White City. And that would be the first permeable pavement that has high strength potential to be used for highways and other elements of airport assets like taxiways, aprons, and stand. It has major environmental benefits to the UK and globally, and it provides a significant contribution towards net zero by 2050. And we are currently working with a number of major players, including National Highways and a number of different airports like Gatwick Airport, to deliver this technology at critical infrastructure. And this will hopefully enable the widespread adoption of permeable pavements, and we would be able to become a permeable city that is capable of addressing the challenges that we're going to be facing as a result of climate change. Thank you very much for listening, and I would be happy to take questions now.